Hi everyone, welcome to another video in my channel, and in this video we are going to discuss about system calls in Linux. We will try to understand how system calls are invoked in the Linux operating system, and we will also try to invoke a system call without using the libc library. In short, we will try to mimic whatever the libc library does in order to invoke a system call. So yeah, without further delay, let's get started. Okay, so the first thing we need to understand is what are system call, and in order to understand that, we will take help of a tiny C program. Let's say we want to print something on the screen. So for that, the C program will be something like this. Instead of doing the normal printf, let's tweak it slightly. Instead of using printf, we will use the write call or the write function call, because at the end of the day, printing something on screen is also pretty much writing to the standard output, right? So we are pretty much writing out to the file descriptor 1 for the program. So we will include unistd std.h, and it will be a pretty tiny program. So let's say our message is something like this: hello from Isotech. So the write call returns us the number of bytes written to the files. We will have a variable to store that, and we will invoke the write library call. The first argument it takes, it's the file descriptor. So in this case it will be 1, then the buffer from which it will read the message, which in this case will be our message pointer, and the number of bytes to write. So in this case, the number of bytes we want to write to the file is 20. I just manually counted it to keep it simple. And that's it. Let's write a tiny makefile to compile this program, and also we will be using this makefile to compile the future code we will be writing. So let's call it build hello, and we will do gcc-o hello.c and run hello, which will simply run it. That's it. And let's build it. Build hello, and we will do a run hello. Yep, so we got our message hello from Isotech. So coming back to our original question, what are system calls? So system calls are routines baked into the kernel which operate in the privileged mode, and we need them to perform anything and everything in the Linux operating system. So let's say we want to open a file, write something to a file, like in this case, or we want to open a socket, we want to read from a socket. For anything and everything like that, we have to take help of these kernel routines called system calls. So they are pretty much the interface that the kernel provides to us, to the userland programs, when we want to use some of the services provided by the kernel. So as I mentioned, here in this program, the major system call we are using is the write system call, because we are writing something to the file. People often think that this write call that we invoked here from unistd.h, this write call is the actual system call that is being called. But that's not at all the case, because this write call is working in the userland, and it's located in the libc standard shared library, which is linked to all the programs when they are executed in Linux. So this is not the system call, but this is a wrapper on top of the actual system call that's present in the kernel. And this also implies that this program is pretty much useless. We cannot run this program without the presence of the libc shared object or the libc standard library, because without that we don't have the definition of this write library call, right? So our program won't be able to invoke this write call. So we can verify this. If we can simply do a ldd hello, we will see that it's linked with this libc.so.6. Another way to verify this is if we do a readelf. So readelf is a pretty handy utility when you are working with else or elf file format. If we do a readelf-d hello, and then we grep for something like needed. So basically using this -d, we are reading the dynamic link section of the readelf file, and what we will find in that section is that the section clearly mentions that this program requires libc.so.6 to function, right? Now the question is, the most important and interesting question is, if the actual write system call is a kernel routine which operates in the privilege mode or ring 0, how does a userland program which has lower privileges, like our program running in the user space, is able to invoke a kernel routine, right? So that's what we would try to understand here. So if we check the header section of this ELF file generated, which is hello, let's do that quickly. We will see that it's using something called the OS ABI, and this is system V, right? Now what we need to understand is, what is this system V ABI, right? So ABI stands for the application binary interface. So this application binary interface is a specification, or rather a set of rules, which mentions various things like how are functions supposed to call each other, more importantly how the parameters will be passed between the functions at a assembly level, or how will dynamic linking work, or how the ELF format will look like. All these low level things are provided by this system V application binary interface, right? This is very much processor dependent. Different processors use different flavors of this application binary interface. How a userland program will invoke a system call which works in privilege mode is provided by this system V application binary interface. So in this case, out of all the various things mentioned by the sysv, so system V application binary interface is also in short sometimes called the sysv ABI. As of now, we will only try to focus on the interface and how functions are supposed to be called as per the sysv ABI for x86 and x64 systems. So depending on the processor architecture, there is majorly two ways in which we can pass parameters between different functions or different kernel functions at a assembly level. So majorly, one way is to use the stack, that is the caller function pushes the parameters into the stack and the function that is being called pops them out of the stack. This is one way. The other major way is to put the parameters into the register. So the caller function puts the parameters into certain registers and the called function gets these out of the registers and does its work, right? Specifically for Linux system calls, what the caller function is expected to do is put all the parameters for the chosen system call routine in the registers EBX, ECX, EDX, and so on, the general purpose registers in case of x86 systems, and in case of x64, the registers it's supposed to put them into are RDI, RSI, RDX, R10, R9, and all those registers, right? And so on. And finally, what the caller function will do is it will put the system call number corresponding to the system call it wants to invoke into the accumulator. So for x86 it will be EAX, and for x64 it will be RAX. Now at this point, what the caller function will do in order to invoke a system call routine is, in case of x86 systems, the caller will simply invoke the hex 80 interrupt or x80 interrupt, and in case of x64 it will call the syscall instruction in assembly. And this is exactly what is being done by this write library call wrapper. So all these things is, all these details which is very much processor dependent and low level, is hidden away from the user or from the userland program by this write library call, so that libc takes care of this and users don't have to worry about these things. So let's try to understand this visually once. Okay, so first what we have is the userland. Then we have the boundary between the user land and the kernel land, and then we have the kernel space. Now this boundary is very important because all the programs running in kernel space are running in privileged mode, or rather they are running in the ring 0 of the CPU. So this is also the privileged mode. Okay, so now what we are interested in is the write library call, which is located in libc. So as we saw, it takes the file descriptor, the message buffer, and the length of the string, or the length of, or the number of bytes we want to write to the file descriptor. So now what this write library call will do is, via some function call chains, it will follow the sysv ABI, the sysv application binary interface, and depending on the architecture it's running on, whether it's x86 or x64, it will do one of the following things. So if it's x86, what it will do is it will put these parameters into the corresponding desired registers. So the registers that it will use in x86 is EBX, ECX, and EDX, right? And in EAX, it will put the syscall number, right? And in case of x64, it's pretty much similar, but the registers will differ. So in this case, the parameters will go to RDX, RSI, and RDI. And finally, it will in RAX, which is the accumulator under x64, it will put the system call number. System call number. Okay, after it has done these things, in case of x86, it will invoke the x80 interrupt, it's basically the hexadecimal 80 interrupt. And in case of the x64 system, it will call the syscall instruction, right? Now, both this will have similar impact, although the approaches are different, and also this syscall instruction is a bit faster than the interrupt approach, but both of these will essentially have similar effect, and that is both this interrupt call and the syscall instruction, what they will do is it will put the current process, let's say this program which calls the write library call is running as a process hello, then it will put hello to sleep. And from this point onwards, the boundary cross will happen and the kernel will take over. So the first kernel routine that the Linux kernel will invoke as a response to this x80 interrupt or this syscall instruction is the syscall handler. So syscall handler is pretty much the entry point for the system call into the kernel. And what this syscall handler will do is it will first read the value present in the accumulator, which is EAX or RAX as the case may be. And from there it will get the syscall number. And once it knows the syscall number, it knows which system call kernel routine to invoke. In this case, it will know that the routine it needs to call is syswrite. And what syswrite will do is it will simply read the registers and it will get its call parameters. And then it's a whole separate story. It might do several things. It might access the VFS functions, or the routine might access some of the device drivers, anything and everything, whatever the system call demands. So that's pretty much the flow and how the system call is ultimately called, starting from the libc library call, right? And it's the responsibility of the GCC, a compiler on a particular processor architecture, to generate this section of assembly code in the compiled program corresponding to this write library call, which will do this function of putting the parameters into the correct registers. So GCC will take care of it and it will generate this desired assembly section or the assembly code for the parameter assignment to the registers. So now we'll see how we can write a tiny assembly program which can directly call the system call without taking help of the libc. And as the assembler, I will be using NASM, the NetWhite assembler. It's pretty easy to use, and that's why I chose NASM. Also, I'll be doing it for the x86, but at the end I'll also show you how it works on how it can work on the x64. It doesn't really make any difference we follow x86 or we'll follow x64. The concept we are trying to understand here is kind of the same for both. Let's start with the x86 approach. So I'll first create a file called main.asm and let's quickly write our tiny assembly program. So first we have this thing called section.data. So first we will define our message and it will be of type db or byte, and it will be hello from Isotech. I believe let's keep it same. Yeah, I believe it's same as this one. Okay, and also we will put a carriage return and a string terminator. Okay, then what we want is the length of the message, of course, in order to use the write system call. So for that, what we'll do is $-msg. So we are simply creating a symbol called len, whose value will be the current address, which is, or the current instruction address, which is dollar, minus the address of this label called msg, and that will pretty much be the length of this string. Okay, so next we start with the text section, which is also the code section, and we will define the start symbol, which will tell the kernel where to start executing our assembly program from. And let's define the start symbol. So first, okay, so for the write system call, what it demands is the edx register. In case of x86, it will have the length of the message, or the length of number of bytes. So here we will move the variable len, or the data len. Then it says that in ecx it should have the address of the message or the buffer, and in ebx we should have the file descriptor, which is 1 in case of standard output. And finally, as I mentioned, in eax we will have the syscall number. For in case of write, the syscall number is 4. And finally we will invoke the hex80 system call. We cannot end here actually, because whenever a C program exits, the exit system call is automatically called, or else we will get a segfault error. So let's quickly call sys exit system call, which will make sure our program ends gracefully. So that's pretty easy. For that, in ebx we will put 0, in eax we will put 1. 1 is the system call number for the exit system call, and once again we will call the hex80 interrupt, right? Okay, and now what we will do is we will create a tiny makefile. Oh, my bad, the makefile is already there. So let's do build x86. Let's give underscore here, and what we'll do is nasm -f elf. By default, if you give elf, it takes 32, and the 32-bit or the x86 architecture. And we'll do main.asm, and we'll have to link it as well in order to provide a elf file which the kernel can execute. For that, we'll do ld-m elf i386 main.o main, and we will do a run x86, which will simply run it. Okay, so now let's try to run it. So we'll do a make build x86, and the main file is produced, and main elf file is produced, and let's try to run it. Run x86, and it runs, and we have got our message hello from Exotic, which is exactly same as our, I guess it was run hello, which is exactly same as our C program. So now if we try to do the same things that we did on the C program, what we did there was we did a readelf, and we did -d main and grep. For what we'll see is that it doesn't have any dependency on the libc shared library, so no dynamic linking is happening. And also if we do this, so it clearly mentions that there is no dynamic section in this file, so which means our program is not at all dependent on libc, and it's completely able to call the system call itself. So this is how the actual system call is being called. The actual system call kernel routine is been called from our program, or from any program, or rather this is actually what the write read library calls present in libc does in order to invoke our system calls. So let's quickly see how this will look on x64, right? So I'll quickly create a file called main64.asm, and it's pretty same, to be honest. So I mean, of course the registers changes, but the structure remains pretty much same. So I'll simply copy this and I will paste it here. And now let's see what's the differences. So edx becomes rdx, ecx becomes rsi, and ebx becomes rdi. Again, remember, we don't have anything to do here. Everything here is provided by the system v abi, or the system v application binary interface. We are just following those rules. And finally rx, the other thing that changes here is in x64 the system call number changes. It's no more 4 but it is 1. And of course we won't be using the interrupt anymore. We will use this syscall instruction, and instead of eax we will get rid of this, and instead of eax, again in rax we will put, instead of 1 was the system call number for exit system call on x86, but on x64 the system call number for the exit system call is 60, and we will call the syscall instruction. And that should be it. Once again, let's change our makefile. So let's again copy this and we will call it x64. It has to be elf64, and of course it's main64.asm. and then for ld, what we will do is ld-m, instead of elf-i386 what we'll do is x86 underscore 64 main64.o, and this shall produce main64. Okay, so that's it. Now let's try to compile and run it. We'll do a make build x64, and it got compiled, and just let's now run it, and it's the exact same message that we got from main, right? So this is the 64-bit version of calling system call directly from our program in assembly. So yep, this is what I wanted to discuss and show in this video, how a system call in Linux is actually called from the user space. So this is it for this video. Thanks for watching and see you all next time.